Hello everyone, welcome to Megger's monthly webinar series. Today's topic is Understanding the Recommended Practices of Load Testing. In this session, we'll be discussing the differences between IEEE and NERC battery testing recommendations and the elements to consider when designing a test program. My name is Yer To, and I'm the Marketing Communications Engineer for Megger North America. And I'll be acting as the moderator for today's presentation. I'll be supporting you on any technical issues or questions for our presenter during the session. On the right-hand side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segments. You'll receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Damien Robinson, Megger's Southwest Regional Sales Manager. Damien is based out of Austin, Texas. Thank you for joining us, Damien.
Thank you, Yer. And thank you for everyone who's attending. I will say that, as Yer mentioned, I'm a Regional Sales Manager. I hope to be able to answer all the questions that are presented. I do want to preface that I am a bit more of a generalist for Megger, so batteries are not my exact specialty, but I do have a good knowledge on it. If there's something that I don't know, I promise that I will take those questions and give them, provide them back in a written format. Okay, so our agenda for today, the first thing we're going to do is a brief review of the purpose of a battery. The two technologies that we're going to be discussing are the VLA, or vented lead acid, and the valve regulated lead acid batteries, which are the majority of the batteries out there, and the common tests that are performed on batteries. We will then go into the IEEE capacity test recommendations, the different types of tests we'll do, and how you use those to design a test, the effects that we need to consider when we're performing the different tests. Then we'll do a quick review of what the results will look like provided by the Megger solution, and just do a quick review of the NERC recommendations and compare those to what IEEE recommends. So with that, the purpose of a battery is obviously to support a load based on a loss of a power or as part of a protection system, such as opening a circuit breaker. Now, when we look at a battery, we're always provided what kind of load it would support based on a rating of ampere hours. Batteries, it depends which kind you select, but they're rated at a certain amount of current for a specified amount of time. So, for example, a 120 amp hour battery could be 15 amps by 8 hours, and that is at 77 degrees Fahrenheit or 25 degrees C. Battery manufacturers also provide that specification. Now, one thing to point out, and we'll see some examples later, is that this is not a linear function. So I can't take half the time, say 4 hours, and get 30 amps. It doesn't work that way. The amps actually decrease when I decrease the amount of time, or they proportionally decrease, I should say. Now, the VLA is vented lead acid battery. The VRLA is a valve regulated lead acid battery. You can always, vented lead acids are also called flooded cells or wet cells. You can always tell the difference between those and valve regulated because they will have the tank or the jar where you can actually see through it, like these here. And then the valve regulated, they're also called sealed or maintenance free, which they are not truly sealed and not truly maintenance free, but they're just containers you won't be able to see through to be able to see the plates. They're both going to be some sort of lead alloy base or pure lead, and then there are some differences, such as the flooded cells, you obviously have liquid in it, and then the valve regulated is going to be some sort of absorbed glass mat or like a gel cell. Now, some of the similarities and differences. Now, obviously these are not necessarily all of the similarities or all of the differences, and nor is this intended to indicate to you what specific battery you need for your application. But just some that I wanted to point out. You're going to have a similar construction between the two, with the plates being a grid base with an based on some sort of alloy, lead alloy, and a paste material. As well, they're both going to be using sulfuric acid with our formula of how they operate down below, where the lead is going to be my negative plate, the lead oxide is going to be my positive plate, and then I'm going to have some sort of sulfuric acid, and obviously this is in the charged state. And then in the discharge state, both of my plates are going to become sulfated, they're going to become lead sulfate, and then I'm going to get some water. Now, the differences is going to be size. The vented lead acid is going to always proportionally be bigger than a valve-regulated lead acid battery. The general stability in life, vented lead acid batteries generally are more stable, and generally you get a longer lifespan out of them, given the approximate same conditions. The electrolyte level is also a little bit different. Valve regulated tends to be a little bit higher. A higher electrolyte level, measured as in terms of specific gravity, typically means that you're going to get a higher power out of the battery or higher voltage. As well, the recombination rate of oxygen and hydrogen, and basically that means how much of the oxygen and hydrogen is remaining, whether you're going from charge or discharge, how much of it is remaining within the battery and how much is being vented out. You'll see that the vented lead acid batteries, or your flooded cells, they're not quite as efficient, so they're constantly leaking this oxygen and hydrogen, where the valve regulated lead acid, they have a lot better efficiency. One other difference that I did not put on here is the separator is different. The vented lead acid batteries use a microporous material so that you have a good electrolyte and gas flow inside of the battery, whereas a valve regulated, for example, might use absorbed glass mat, where the acid is fully absorbed into that glass mat material, and that glass mat must maintain contact with the plates of the battery. Okay, some of the common tests. You have monthly and quarterly and annual tests, and this is specifically for the vented lead acid battery based on IEEE standard 450-2010. You'll see that on the monthly basis, you're going to be doing some of your voltage checks, charger output, your specific gravity measurements on pilot cells and things of that nature, checking for grounds. Then you get into quarterly, you're doing more cells with regards to temperature and specific gravity, and you're going to do all of your cell voltages. And then when you get on an annual basis, now you're doing the specific gravity of every cell, your strap resistances, the battery rack integrity. And we'll talk more about cell ohmic values in another couple slides, but this is one, it's optional, which is interesting to me for this specific type of battery, but it's one that it can be a lot of value, so it's one that I do highly recommend. Now, all of these tests are to assure that the batteries are going to be in good operating condition and that you'll have the best chance of getting the maximum amount of life out of them, as well as the safe operation of the batteries. Now, when we switch over to the valve-regulated lead acid, this is what's in the IEEE standard 1188-2005. You'll notice that on a monthly basis, there's less items for me to do. The visual's still there, the float voltage, charger output, temperature, ventilation, all those things are still there. But I don't have the specific gravities because I can't get access to the battery, to the electrolyte within the battery. So all of those are gone away. But you'll also notice that the grounds are gone away, the unintentional grounds. However, it is stated as part of the precautions within the standard that you are to verify the voltage to ground before you begin any work. So if you follow the standard, you're still going to notice if there's any unintentional grounds by doing that test as well. Typically, these chargers are going to have some sort of ground fault indicator in them as well. Now, you'll notice also on the cord, with regards to the cell ohmic values, they've now moved from the annual column, and they're no longer optional. They're now in the quarterly column, and they're no longer optional. That goes back to a statement I mentioned earlier that, generally speaking, valve-regulated lead-acid batteries are not as stable as your vented lead-acid batteries, and so these cell ohmic values become a very valuable trending tool for you. Now, there's a couple terms I want to introduce. You may be familiar with these if you attended one of our previous battery seminars, but we talk about state of charge, and that's an indication of the battery's charge level. The two main measurements that people use for that are voltage or specific gravity. And if we take a look on the right-hand side where I have my D battery, C battery, AA, and AAA batteries, if I were to take a voltmeter across all of them, I'm going to measure 1.5 volts. But obviously the ampere rating is different for each one of them. As I go up in size, I'm getting more capacity out of them. However, but a state of charge doesn't tell me necessarily what my capacity is. So there's also state of health. Now, this is an indication of the battery's overall health, and it correlates to load. The value that we typically use for these measurements is my cell ohmic values. And the trend, how they relate, is that as my ohmic value goes up, my capacity or ampere rating tends to decrease. And I have a couple of pictures there of our battery impedance test products called the Byte series that we use for that measurement. Now, this specific test, it is a trending test. And some of the things that you'll want to do, this is just a sample of a table that you'll use where you can check the averages of, say, a flooded cell versus an individual cell versus the string average, an individual cell versus the last test date, so how much did it change from 2015 to 2017, and then how much has changed versus, say, the baseline. So at some point I'm going to reach my minimum value, and then it's going to trend up from that point. And how much has it changed from that? And that could have been 5 years ago, 6 years ago, 10 years ago that I received that value. And what you'll see on a trend, on my x-axis I have the percent of battery life versus the percent impedance change, and I have 3 different conditions that can occur. The blue trace being a normal cell, that it starts out all of them start out a little bit high, they'll fully form and come into some low value, and so right here where kind of my laser is, that would be considered my baseline. And then normally, under regular conditions, they should remain fairly stable but slightly increasing up until a point where you get, towards 60, 70, 80%, and then they start taking off, trending towards an open cell under normal conditions. A weak cell would follow that same pattern, but they would just fail a lot quicker. And then some sort of abnormal cell where you might be having excessive sulfation, it will trend downwards. In other words, it's trending towards a short, which is that's not the normal process a battery takes. Now, I mentioned that this type of test, it's a trending test. As my ohmic value goes up, my capacity goes down. But if I have an ohmic value that increases 10%, I know that my amp hour rate decreased, but I don't know to what degree. So the only solution to this problem is to do a capacity test. So when we look at the IEEE capacity test recommendations, there are 4 types. There's an acceptance test, performance test, a service test, and a modified performance test. Now, it should be noted that the modified performance test is only recognized for the vented lead-acid batteries in the IEEE 450 standard. It is not recognized for the valve-regulated lead-acid. Only the acceptance, performance, and service tests are. Now, the general purpose, and we'll get into these in more detail, but the general purpose is the acceptance and performance are to determine the capacity of the battery. The service test is to verify the battery's ability to meet its duty cycle. In other words, what the engineer designed it to the load that it was designed to carry for the specified amounts of times. Now, the modified performance test is to determine capacity, and it's also to verify the ability to meet the critical part of its duty cycle. And we'll get into that more in a few slides. The acceptance test is made at the beginning of the life of the battery when it's brand new. Typically, it's going to be done upon installation or possibly even at the manufacturer site. This test is usually done on a constant current, although you can use constant power as well. It's just generally easier for whatever instruments you're using to do a constant current, so people tend to gravitate towards that. There are some tests that you're typically going to do with all of these. Really, you're going to monitor your voltages, your electrolyte levels, and specific gravity prior to doing any sort of test. This test is going to be considered successful if every cell is at least 90% of what the manufacturer designed its capacity to be. Now, after this test, you'll do a performance test, which we'll get into the next slide, and it might be noted that the performance test lasts longer than this first acceptance test. As I mentioned, this is considered passing at 90%, whereas you'll go to the next test and it could be 100 to reach that 100% capacity design. A performance test is much like an acceptance test. It's a constant current or constant power test, but this is made after the battery has been in service for some period of time, typically 2 years. It's recommended, according to the IEEE, to do this test to make sure that your duration is similar to that of the duty cycle. And you'll want to do these on a continuous basis, and we'll get into the frequency in a few slides, what the recommended frequencies are. Now, the service test, as I mentioned, is going to be based on the ability for the battery to meet its load. In other words, what it was designed to carry for the amount of time it's designed to carry. You're testing exactly to those specifications. Now, one of the differences with this particular test is it's done in an as-found condition. So we're not going to equalize the batteries prior to the test. The other important thing, we haven't talked about the effects of temperature or age yet. We will get to that, but you will not do this test and correct for temperature or age. It's completely in an as-found condition. The modified performance test is also a test in the as-found condition. Now, it has a twofold process where you're going to do combination of the high rate, the highest rate typically shown for what it's designed or for its duty cycle, as well as the duration, the full duration, the full capacity, or the full load that I need to get out of this, that I need to support with this battery. So we're going to confirm both the critical period of the low duty cycle as well as what the percentage rating of the capacity is. This can be done in lieu of a service test or a performance test at any time, and it's considered passing if it has a rated capacity of 80% or greater. Now the frequency, as I mentioned, yes.
Before we move on, I have a couple questions from the audience.
Sure.
So if you are continuously monitoring and trending the cell ohmic value, then how often should you perform a capacity test?
If you're monitoring the cell only, repeat the question.
Ohmic value. If you're continuously monitoring and trending the ohmic value, then how often should you perform capacity testing?
So, and actually that's what this slide gets into. With the ohmic value, yeah, you're gonna want to do that at a minimum annually. I mean, for vented lead acid, definitely you're gonna want to do that annually, and for the valve regulated lead acid, you're going to want to do that quarterly. But for vented lead acid batteries, you're going to want to do the test within the first 2 years of service, and then you'll want to continue to do tests every 25% of the expected life. So the interesting thing about this is that battery manufacturers might say that this is a 30-year battery, but you're not necessarily going to get 30 years of life out of it. So you have to take into consideration the amount of life you realistically expect to get out of it, which might be 20 years. So if I do 25% of that, then that's going to be every 5 years I'm going to be doing a test. So I gave an example here where if it's based on a 16-year life expectancy, I'm going to do every 4 years. Now for valve regulated lead acid batteries, it's not to exceed 25% or 2 years, whichever is less. And that again goes back to the stability of these types of batteries. They're not as stable as your flooded cells, so they have typically a lower life expectancy. Hopefully that answered the question.
Okay, and then what would be the best way to test AC ripple?
The AC ripple, so there's actually two different quantities that you can look at. There's AC ripple current and there's AC ripple voltage. With AC ripple voltage, you can just get a simple voltmeter, so it's not that difficult. With AC ripple current, that's actually not too challenging either. It's, especially for us, our bite testers actually do that measurement for you, both the bite 3 and the bite 2. One with the CT clamp, one by going on to one of the straps and just measuring it. But generally speaking, what you need is you need an AC ammeter and some sort of clamp or some sort of way to get into the circuit or into the series path of the battery string.
Great.
Okay. Now, we've pretty much covered all this slide. However, there's one other important part at the bottom where it talks about annual testing, which is recommended. So you have your normal recommendations of 25% of life or 2 years for whichever is less for the VRLA. But if you start seeing signs of degradation, then you will want to test on an annual basis, and the break point is right around the 85% of life of expected life. Oops, sorry. Okay. Now there are some conditions that need to be met based on doing an acceptance or a performance test, and you're going to follow these steps as well. You're going to follow them for the service and the modified performance test, with the exception of item number 1, where you'll want to equalize the battery and then return it to float for a minimum of 72 hours prior to the test. But just remember, the service test and the modified performance test, they're in the as found condition, so we do not equalize. But the rest of the measurements still apply, where you're going to go through and make sure that your battery connections and your strap resistance measurements are adequate so that you get the most realistic test. You can record your float voltages and currents and your electrolyte levels if you're using vented lead acid of at least 10% of the cells. Your terminal float voltage as well. When we get to VRLA, we're going to want to do the ohmic values. And I need to take any other necessary precautions, whether it's isolating the battery from load or isolating it from a parallel battery string or something of that nature, so I don't jeopardize my system or any equipment that may still be relying upon the battery. Now, some of the effects we need to consider. One of the big things we need to consider is temperature. I mentioned earlier that a battery manufacturer gives the rating of the battery at a certain temperature, which is 25 degrees Celsius or 77 degrees Fahrenheit. As the temperature decreases, my amp hour decreases. So there's a graph here that shows exactly that, where at 25 degrees C, I'm at 100% rated capacity, but as I drop in temperature, my capacity goes down. Whereas if I go up in temperature, my capacity or my amp hour rating goes up. So one might think, well, okay, well, if 77 degrees is good at 100%, maybe I can go to 30 degrees and get 105%. Well, the problem there is that for every 10 degrees C rise or 18 degrees Fahrenheit rise in temperature, it decreases the battery life by half. So the 77 degrees or 25 degrees Celsius is, kind of the ideal point. So any deviations from that 25 degrees Celsius, 77 degrees Fahrenheit has to be adjusted in my capacity calculations. And there's two ways to address that. There's a time-adjusted method and there's a rate-adjusted method. And we'll talk about that next. Oh, sorry, one second. Okay. The time-adjusted method is recommended for your acceptance tests, your modified performance, and your performance tests with a duration of 1 hour or greater. So for most substation applications, generation battery applications, you're going to be doing a minimum of a 1 hour test in most of those situations. So you're going to use this method. Some of the UPS applications you might use a rate adjusted method, which we'll talk about in a minute. But you'll choose the test current based on the manufacturer recommendations, and you're not going to make any adjustments to the test current. What you're going to do is you're going to adjust the capacity. So I have my calculation down here to calculate percent capacity. And what it is this TS is say I was doing a 1 hour test, I would look at the battery manufacturer's discharge rate schedule, and it'll give me that specified rate for that specified amount of time. So this is the time portion related to whatever current I'm going to be doing. And then this is the actual measured time, TA. And then I'm going to apply a temperature correct value, multiply that by 100, and that's going to give me my percent rated capacity at 25 degrees C. And this is the values, and you'll notice that at 25 degrees C, obviously my correction value is 1. I don't need to do any temperature correction. So I'll just basically do the time that the battery discharged divided by the time it was specified to discharge. If I go down in temperature, you'll see my temperature corrections are going down, and then if I go up in temperature, you see they're going up. Now, the rate-adjusted method is for a performance or an acceptance test of 1 hour or less. And typically, these are going to be your UPS applications, like, for example, maybe in a data center or something of that nature. Now, this discharge rate, you can do it one of two ways. You can either simulate an end-of-life condition based on some sort of aging factor. Basically, what an aging factor is whenever engineer is designing a battery, they're designing it to last so long, so they actually oversize the batteries in the beginning so that once it reaches that end-of-life schedule, it's able to supply the amount of load for the exact amount of time that I want. So they call that an aging factor. So you can simulate an end of life based on the aging condition, or you can actually run it at the full published rate. So for example, if the battery manufacturer said, run this test for 30 minutes at 200 amps, then that's what you're going to do. Whereas if you're simulating an end of life condition, it might be 180 amps instead of 200. The only other time you adjust the rate of current is if the temperature range is outside of 15 degrees Celsius or 35 to 35 degrees Celsius. As long as it's within there, you don't do anything else with the rate, the test current rate. And my calculation, you'll see it change a little bit. Instead of the temperature correction portion being in the divisor, being in the bottom portion, now it's on the top, where I have my actual rate and instead of being time this time, now it's actually current, and then I have my published, what the published rating is. Got my temperature correction, multiply that by 100, and that gives me my percent capacity. And you'll notice that the first one had KT as the reference, and now this one has KC, and it is a completely different table. You cannot interchange the two, so it's important to make sure you choose the right table for the right method. And you'll also notice that obviously 25 degrees C, I'm at 1. If I go up in temperature, now my values are going down instead of going up like before, and if I go down in temperature, my values are going up. Now, one of the biggest questions I always get when it comes to capacity testing is this a destructive test? And no, it's not a destructive test. It doesn't destroy the batteries. Now, it is a consumptive test. It does consume some of the life of the battery. There are a couple terms that I want to introduce to you. One is called depth of discharge. And this is equal to how deeply a battery is discharged. So, for example, kind of think of it as the opposite of a charge state. If you look on your phone and you have it plugged in, it might say 90% charged or 80% or 100% charged. Well, if I'm at 100% charged, that means I'm 0% discharged. Whereas if I took, say, 10 amp hours, or I consume 10 amp hours out of a 100 amp hour battery, now I'm at a 10% depth of discharge, or a 90% charge state. Now, this is important because battery manufacturers will say that their batteries are designed for so many cycles, and a cycle is defined as one complete period of discharge and recharge. Now, the other interesting thing is that not necessarily 100% charge is considered a cycle. You have to look at the battery manufacturer. Typically, around 80% depth of discharge is considered one cycle. And these are just some samples here where vented lead acid might have 20 deep discharge cycles. They don't like to be cycled quite as much as a valve regulated lead acid, where I found an example where one said it claimed to have 1,600 deep discharge cycles available. Now, so let's go through an example on the depth of discharge. So I have a 50 amp hour battery, and my load profile requires 24 amp hours. So I need to remove 24 amp hours from this 50 based on my load criteria. So this is an example of a discharge curve, and we're not going to look at the minutes. We're going to be looking at the hours. I'm using 1.75 volts per cell at 77 degrees Fahrenheit. Mention that battery manufacturers will have various different types of volts per cell that you can use. 1.75 is very common. That's probably the most common. But they also might have 1.8, 1.85, or various different levels, and that will change these discharge currents here. So then I have my time across the top, how many hours do I want to do, and then it tells me based on this specific battery, the 50 amp hour battery, what my discharge rates will be. And as I mentioned earlier, they typically will rate the batteries for a specified amount of time. So this is an 8-hour battery, where if I took 8 times 6.3, that's going to give me my 50. Whereas if I cut it in half to 4 hours, it doesn't double to 12.6, it actually goes to 10.4. That's showing that nonlinear function. Now, scenario 1, to do this test, let's say I chose the 1-hour rate of 25.5 amps. So I removed 25.5 amps from the battery. My depth of discharge is only 51%. Scenario 2, I say, all right, I want to use the 3-hour rate, which then removes, I have to do 12.9 amps, and that removes 38.7 amp hours from the battery. And I have to take the 38.7 amp hours divided by the 50 amp hour capacity. I'm now 77.4% depth of discharge. Now, what I'll say is both tests are valid, but as you can see, the 1-hour rate is less consumptive in nature. So I'm using about a half of a cycle versus 3/4 of a cycle. Now, another effect to consider is what's called cell reversal. That's when one cell, instead of being in the right polarity, it actually switches polarity. Instead of supplying capacity, it's now actually becoming a load on the battery string, which means that the battery string is not going to last as long as I wanted it to. So a cell is considered to be approaching cell reversal when you reach 1 volt or below. If you reach that point on a particular cell and you still got some time to go on your test, then you should bypass that cell. Now, when you're bypassing a cell, you have a maximum of 10% of the test time for 6 minutes, whichever is less. So it's basically for a 1-hour test, you have 6 minutes, and for a 2-hour test, you have 6 minutes. But if you're on a 30-minute test, then you only have 3 minutes to swap that battery string to bypass that cell. The other thing to note is you're only allowed 1 pause during the test. So if you stopped it halfway, bypassed a few cells, and then 3/4 of the way into the test you have some more cells you need to bypass, well then that's a non-passing test. You're not allowed to pause more than once. Now, the important thing is that once you bypass a cell, you then need to recalculate what's going to be your stop condition of the voltage. So, for example, if I started with 60 cells, but then I had a stop end voltage of 105 volts, now 59 cells is going to be 103.25. So now we get into some of the aspects of the test design. There's another guide called IEEE 485. Presumably, everyone's familiar with this. These are some of the parameters that you need with regards to sizing a lead-acid battery. And they'll ask things, you'll consider things such as the application being switchgear, generation, data center, what type of temperature the battery is going to see, what's the end voltage or the minimum volts per cell that I need, what design margin I'm going to incorporate, and so I can account for potential site growth, and what kind of aging factor am I going to use. All of these are basically designed to oversize the battery so that when it reaches end of life or it's nearing the end of life, you still have enough capacity. So from a engineer, I will then receive something like what's shown here. I'll have my sizing parameters, which had all the information from the IEEE 485 guide, as well as what my load profile is. Now, some info for consideration on this is I have my minimum voltage of 1.75 volts per cell, so that's what I'm going to need that for my test criteria. I also have my amp hour required based on this information in my load profile. I have period 1 of 1 minute at 100 amps, and then 239 minutes at 18 amps. And admittedly, this is a very simplified load profile. Yours might be more complex than this, but I just wanted to give an example. So to calculate the amount of amp hours required, I'm going to convert this time into an hour basis. So I need to divide the 1 by 60 and then multiply that by the current. As well, I need to convert this into hour basis, period 2. So I take my 239 divided by 60 and multiply that by my 18 amps, and that gives me that I need 73.37 amp hours of capacity for this battery. I also have my maximum current. I'll need that for a particular test. I have my total time duration of 4 hours, and then I also have my aging factor of 1.25. So for this particular test, I'm assuming we made the assumption based on the design that we determined 150 amp hour battery would be sufficient for my needs. So if I'm looking at an acceptance or a performance test, I need the 73.37 amp hours, so I can take the 1 hour rate and see that that's going to provide me 76.5 amp hours, which will verify that I'll be able to get the 73 amp hours that I need out. And I see that I get a 51% depth of discharge, so I've used about half of a charge cycle. When I look at a service test, again, remember this is in an as-found condition, and it's just based on the ability to meet the load. So I'm going to follow the load profile exactly of 1 minute at 100 amps and then 239 minutes at 18 amps. And I've already calculated the 73.37 amp hours, and that's a 48.9%, or roughly half of a depth of discharge, so half of a cycle. Now, if I do a modified performance test, this one gets a little bit more complex. The first thing I have to do is I have to figure out the amount of test duration that I need, and I don't actually do the 4 hours. What I do is I take into consideration the aging margin that I use in the design criteria. So that means I need to take the 4 hour duration times the 1.25, and I'm going to do a test of 5 hours. Additionally, I need to test the critical period of this, which is the 100 amps. So I need to do 1 minute at 100 amps, and then I need to do the published rate for the 5 hour test, which if I look down here is 26.4 amps. So that's what I do for the other 299 minutes of that 5 hour test, is the 26.4. Now that's obviously very consumptive, 133.2 amp hours, and I get an 88.9% depth of discharge. So I've used 1 cycle in that test. Now, I'll mention this is just one variation of the modified performance test. There's at least one other variation, and you'll see Annex I of IEEE 450 for other methods if you don't have this simple of a load profile. Now looking at some sample test results, what I have here is on my x-axis, this is time, and this is pulled from the software that we use called PowerDB. And then on this axis, I actually have my voltage, the y-axis on the left-hand side, and the y-axis on the right-hand side actually have my capacity in amp hours. So this black curve here is my voltage. So this is the beginning of my test, and then there's a phenomenon called coup de fouet, which basically it means that it literally means crack of the whip, but you come down and you reach some minimum voltage, and then it climbs back up, and then it's fairly stable until you get out, and then it starts dropping very quickly. So that's my voltage graph, and then the blue graph, the blue line is my capacity rated in amp hours over on this axis. These solid lines are different warning and stop limits based on capacity or based on voltage. And then you'll also see that we get our measured battery capacity. This was not done at 25 degrees C, so we had the temperature correction, which the software does automatically for you, as well as it automatically calculates the percent capacity. So this was the actual discharge time, 1 hour, 20 minutes, and 19 seconds. So that may have been based on a 1.5 hour rate. Passing, as I mentioned, is typically considered to be 80%. So this would be a successful test. Now, how we do this, we have a load unit that we call the torque, and that unit will connect across the entire battery string with the dotted lines being the voltage measurement that you'll have. This picture on the right-hand side is the first page of the form that you would use, where you can put in all the nameplate data of the manufacturer, what type of temperature correction method are you going to use, and then what kind of test currents I'm going to put in, what my end voltage are, what time duration, and then what my warning and stop limits are going to be based on voltage or capacity or time. Now, while this is great, there's one critical element missing, and that's the individual cells. So, as I mentioned, the torque goes across the whole entire battery string. So, what we have to incorporate are the battery voltage monitors. And these will monitor each individual cell. The way ours is designed is you connect onto the negative terminal of each battery until you get to the final one, and then you connect onto the negative and positive. So you're reading the voltage between these two, which is also taken into account any voltage drop that may be occurring across this strap. All of these then get connected back to the computer, which is and the torque is also, or the load tester is also connected back to the computer, so you get your individual cell monitoring as well. And this is an example of what it would look like. This is just showing 4 cells, where the black bars, or the grayish colored bars, are my initial conditions, and the green colors are my condition of that specific cell. And I can also set up warning and stop limits, with the dotted red line being warning and the solid red line being stopped. As well, we provide tables of what the values, where they started, what the current value is, and you also have some history in there. Okay. Now, as the final,
before we move on, can we fill a couple of questions? There seems to be some confusion about the depth of discharge cycle. So earlier you said something like 51% is about half a cycle. So does that mean half a cycle is 100% or 80%, like you mentioned earlier?
It's actually based on what the manufacturer says is it defines as a complete cycle. One manufacturer might say 80% is considered a full cycle, 80% depth of discharge. So in that instance, yes, 50% would not be half; it'd be about 60% of a cycle, or give or take. Whereas if a manufacturer said 100% depth of discharge is considered a cycle, then yes, the 51% would be half of a cycle.
Okay. And then, so if a battery has 4 times 20% depth of discharge, would that equal to 1 full cycle?
If the battery has 4 times 20%, I'm not sure I understand the question.
Yeah. I don't know. Maybe I'll see if they elaborate in the chat a bit later. And then
okay.
There were some correction tables, I think, a few slides ago. Are these from the IEEE 450 standard?
Yes, they're contained in both the IEEE 450 as well as the IEEE 1188. 450 is for the vented lead acid or flooded cells, and 1188 is for the valve regulated lead acid. I also forgot to mention, we're not really talking about NiCad batteries. There might be some users of NiCad batteries out there. That guide is IEEE 1106. But yes, the two tables are contained in both of those guides, IEEE guides.
Okay, thank you. I think we'll move on and save more questions for the end of the presentation.
Okay. So again, this is not an in-depth NERC review. Just wanted to highlight a couple of things. Obviously, the NERC is for basically anybody touching the transmission grid, so transmission owners, generation owners, distribution providers. And the current standard that applies to battery testing and maintenance is PRC 005-2. You can just do a Google search for PRC 005-2 and it'll pop up. But it's on the NERC website, and it's the title is Transmission and Generation Protection System Maintenance and Testing. Now, there are two tables within there that pertain to batteries. Table 1-4A is for vented lead acid batteries, as boxed out at the top. And you'll notice that as part of that, they have essentially 3 different boxes for 3 different testing intervals, depending on what you're doing. And they define it as a maximum test interval, as opposed to do this monthly, do this quarterly. They only define the maximum interval allowable. So 4 calendar months, you're going to do some of the similar things that you would do almost on a monthly or quarterly basis in IEEE. And then 18 calendar months, you're going to do things that are typically specified within a quarterly or annual basis for IEEE. Now, the one part I did want to point out, they do expect, unlike in the IEEE guide, where cell ohmic values were optional for vented lead acid batteries, in the NERC standard or guidelines dictate that you're either going to do cell ohmic measurements every 18 months, or as I have boxed out, you're going to do a capacity test, a maximum every 6 calendar years. Now, the valve-regulated lead acid batteries is table 1-4B, and it's very similar, but you'll notice that there are some more, there's a 4-month category, but there's also a 6-month category, unlike with the vented lead acid. So again, that all goes back to my statement of these tend to be less stable, where they're going to want you to do the cell ohmic values every 6 months, or you're going to do a capacity test every 3 calendar years versus 6 for the vented lead acid. Now, just a quick compare and contrast. As I mentioned, up to 4 months between more or less visual inspections required by NERC, whereas IEEE recommends monthly visual inspections. You're up to 6 months for VRLA and 18 months for vented lead acid between your ohmic tests, whereas IEEE recommends quarterly, so twice as frequent for VRLA, and annual, 1.5 times as frequent for vented lead acid batteries. Your NERC requirements for capacity, if you opt to do that instead of the ohmic tests, you're looking at 3 years for VRLA and 6 years for vented lead acid, whereas IEEE recommends you do a performance test once in the first 2 years, and then you don't exceed 25% of the life. Again, there are manufacturers that rate batteries maybe 30 years, but I personally would not design based on a 30-year life. You might design based on a 20-year or 15-year. So 25% of life is going to be less than the 6 years. And keep in mind also that if it's VRLA, they're recommending a maximum of 2 years. So the other part to keep in mind is that one is a legal standard that they're using as guidelines for possibly imposing fines, whereas one is a maintenance standard. And so the design of the legal standard is not as aggressive as the IEEE recommendations, and it's it's my opinion that the IEEE recommendations should be followed more closely, because if you're following IEEE recommendations, you're going to meet the NERC requirements, but you're also going to have a better likelihood of finding problems before they become serious. So in summary, as we mentioned, batteries are the function is to support a load. And so with the desire to support a load, the only method to accurately determine the ability to support the load is doing capacity testing. Generally speaking, you're going to want to do capacity testing within the first 2 years, then no more of 25% of life expectancy, and not to exceed 2 years for VRLA. We need to take into account the effects temperature plays on the capacity and how we handle that with our calculations. As we're designing the test program, we want to minimize the depth of discharge, so we're not consuming as much of the battery life or the number of cycles as we're doing this test. Generally speaking, 80% of capacity is the minimum requirement for a passing condition. And just remember that if you have historically only been using NERC as your guideline, it's a less frequent testing frequency than the IEEE recommendations. This is the test equipment that Megger has to help you in implementing such a program. We have our Torkel on the left-hand side, which is our capacity or load box. It's our capacity tester. Then we have our BVMs, or battery voltage monitors, for your individual cell monitoring. As well, we offer the hydrometer for your specific gravity and temperature measurements, and all of those test instruments are consolidated into or at least the collection of the data is consolidated into what we call PowerDB, our data collection software. This is all the contact information we have, and Year might talk about the webinar survey, but the one thing I do want to point out is we also have a battery testing guide that gives you some valuable information that can be downloaded from our website. And that concludes everything I prepared for the presentation, unless there are additional questions.